just filled them out. No, I didn't just fill them out. I mean,
all right.
filled them
So
out.
we're going to be doing the one remaining section of the textbook today, and its rules are pretty straightforward actually. So we don't need a huge amount of time talking about that. On the other hand, Joe is here with us today, and Joe does have a couple of questions about, I think it's some of the story problems or something. Is that the kinds you have problems with, Joe?
I just had trouble with tangent line d of y over d of x and how to figure out values of the tangent.
Okay. Any particular problem?
Yes, actually.
Okay, great.
The problem set that I was unable to complete because of that,
Yeah.
I've only done up to like page 297.
Okay.
But on 263, 119 through 121.
263?
Yeah. I think that was finding the tangent line,
Let me see here.
which I asked about.
Page, okay. Yes. Okay, so page 263, what problem number?
The problem set 119 to 121, which I asked Scott about it, and I think I can do those now.
Okay.
He said the derivative of the function is the tangent, is the slope.
That is the slope of the tangent line.
And then we just need to insert that into the
Yeah.
slope form.
So let's actually do one of those guys, okay? So that we're clear about such things. How about 119? Okay, so this is on page 263. It's a couple times ago, but that's okay. Everybody could use some reviewing and stuff. Hey, by the way, you know what else you owe me? Snow day assignments. I think only one person's given it to me. I think it's Joe, actually.
No, I haven't
Oh,
completed it today.
it was you, Eric. Yeah, you gave it to me. Okay.
But I do have.
Okay, fantastic. Nobody at EVSC's given me any. I think they're all tired of checking on snow day stuff. You know what I'm saying? So that's all right. All right. So this problem here, the equation is for number 19. It was y equals the square root. I'm sorry, 2 times the square root of x. Is that right? 2 times the square root of x plus 1. And what it wants you to do is it wants you to find the equation of the tangent line at some particular point. It says find the equation of the tangent line to the graph at the indicated point. The point happens to be 4, 5. So this is a graph. Let's see, it's the square root. So it looks something like this. And at some point, right about here, we have a point 4, 5. And what it wants to know is what is the equation of this line that would be tangent if I could draw. Okay? All right, so the slope of a tangent line comes from the derivative. So let's take the derivative, and for the sake of argument today, let's do it with that Leibniz notation. We'll use d by dx. So the derivative with respect to x of 2, I'm going to go ahead and write this as x to the 1/2 power plus 1, just to make it a little more straightforward there. All right, well, this is just a simple power rule type derivative. So let's see, it's this times this. So it's x to the negative 1/2 power. In fact, that is the derivative. But just so you know what it is, if that's more familiar to you, it's 1 over the square root of x. All right, so now you have a point and you have the slope. Well, no, you have an equation for the derivative. To get the slope at this point then, we had to plug in x equals 4. So, the slope of the tangent line, let me go ahead and write that out better. How about this? The slope of the tangent line at x equals 4 then is 1 over the square root of 4 or 1 over 2. So that's the slope of this line here. You have a point that the line goes through, and you have the slope. That's where you use that point-slope form of an equation of a line. You know, we always like y equals mx plus b, and that's our favorite way to write a line.
Why
But
can't we go back to that?
what? Well, you can always.
Why can't we just do that?
Well, you can. Oh, Jared, I'm happy that you said that. All right, so we have this place. Let's call this x1, and let's call this one y1. Another way to write this is y minus y1 equals mx minus x1. That's called the point-slope form. And so we can just plug these numbers in. Y minus 5 equals I'm sorry, we have m already. That's our slope. It's 1/2. X minus x1, which is 4. And you're right. I mean, This is not our most attractive way to write a line. So as Jared says, why don't we go ahead and first we'll expand that 1/2 x minus 2. And then pull that 5 over to this side, and you get y equals 1/2 x plus 3. And that would be the equation of this line right here.
Cool.
Yeah!
Great.
It's so great to have Joe here today. I'm like excited that we have a different group than usual.
What's wrong with the regular group? Yeah.
I'm sick of those groups.
Do you not like us?
I'm sick of that regular group of people, the dynamic. Jared's always fighting with one of the twins.
No, it's not one of the twins. It's Matt.
Oh, there's also Matt, that's true.
No, you meant to say Jared's always losing.
Anyway, okay, so you had some other ones. I think in an email message you mentioned ones where you want to know whether the derivative was equal to 0. Was that, did you ever get those sorted out?
Those were the only ones that was not actually able to help.
Okay. Do you have a particular one of those problems to talk about?
I want to say it's 137 through 141 on the same assignment.
Okay.
That has those types of problems. But I got like 7 different assignment sections listed on
Yeah, you get all kind of tangled around.
So
Okay, so let me just look here. What did you think the number was?
137 and 141.
137 to 141. Find the equation to the tangent line at something. Find the equation. These are all just derivatives.
Are those the ones that are exactly like what we just did?
They are 137. They're just find the equation. Oh, wait. Huh. Okay, they're quite like what we just did. Here, let me just do number 137 with you. Find the equation of a tangent line. Oh, it's quite similar, but it's worth you to doing. f of x equals 2x cubed, yeah. F of x equals 2x cubed. There we go, where'd it go? 4x squared minus 5x. What's the coefficient at the end? Minus 3 at x equals negative 1. At x, that's a terrible at, but you know what I'm saying, x equals minus 1. Alright. It wants us to find the equation of the tangent line. Well now, what I would do first, see we don't actually have a point yet. I mean this is a graph of something. I don't really know what this thing looks like. Let's see, it's a cube, so it probably does something kind of goofy like this. Okay. And what it's saying is that x equals minus 1, what's this tangent line, right? What's this equation of this tangent line right here? Okay. We don't yet even know this point. My first step would be to plug x equals minus 1 into there so that we have what this point is. Oh, it's not even that hard. Let's see, that would be minus 2 plus 4 plus 6 minus 3. Would that be right? 12, 10 minus 3. I think it's 5.
Wouldn't that be plus 5, not plus 6?
Yeah. So 9 minus 5 is 4. Would that be right? I think so. Alright, so I think this point right here is negative 1, 4. Then, we're going to need to take the derivative of this thing.
And from there we would just solve it the exact same way.
Then it's not such a big deal. And this derivative is no big deal at all, right? I mean, we're pretty good at that now. Okay, I mean this one doesn't have anything tricky like quotient rule, product rule, any of those implicit differentiation, any of those kind of tricky things in it.
Then it's, I know 149 was a story problem I was looking at.
Okay.
I didn't know how to solve that, but more than likely the tangent stuff is from the next one, which I didn't know how to answer any of those. I think most of that was just the tangent line stuff, which is what we just did.
Okay, so real quick because this is because we happen to have something handy here. I just want to, whether it was in your email or when we were talking yesterday or whatever, you had some questions, or Scott maybe had some questions about when the slope is equal to 0.
That was one of the ones I'm talking about here.
Okay, for number 149? Or-
No, 149 is a story problem.
Okay.
One of the other ones, it was like, find the points on the graph where the tangent would be equal to 0.
Okay. And so, like, do you have a number?
197 to 201 maybe?
197 to 201?
Yeah.
Let me look.
It was one of those from that section. There's 4 different sections.
Yeah,
from
I
that
understand.
section,
197 to 201. Yeah, okay, to 197. Find all values on the graph of this equation where the tangent line is horizontal. Okay, I like that problem. Let's do that one. When the tangent line is horizontal, what is its slope?
0.
0. So what we're going to do is we're going to find the derivative, and then we're going to find the values of x such that the derivative there is 0. All right, so what is the equation in numbers? This is number 197 on page 285. Find all x values on the graph, 3 sine x cos... Here's the equation. It's minus 3 sine x cosine x, I think. All right, if you actually made a graph of that thing, it's crazy. All right, I don't know what it is. A kind of a weird wavy thing, but it changes amplitude all over the place. It's a mess. And they're wondering where the tangent line is horizontal. Well, in order to do that, first you're going to need the derivative. And just for sake of argument, this time I'm going to use that tick mark notation to mean derivative instead of d by dx or something like that. All right. Well, it's clearly going to be negative 3 times the derivative of this. And the derivative of this is clearly a product rule. So it's derivative of the first term. Here's one term. Here's the other term. Derivative of sine, that's cosine, times the derivative of the second, which is cosine, plus the first times the derivative of the second. So that's a minus sign now, because the derivative of cosine is minus the sine. Alright, so unexpectedly it's actually cosine squared x minus sine squared x. Okay?
Wouldn't that just be tangent squared, or could we pull out anyone and make that tangent squared?
How does that tangent squared?
Cosine squared minus sine squared, I thought.
Not that I can think of. I mean, trig has all kinds of miracles in it. I mean, tangent squared in general would, like tangent squared of theta is sine squared of theta over cosine squared of theta. I'm trying to think.
Some sort of property or something.
Yeah, there is. I'm trying to think real quick. There's also tangent squared of theta.
Square equals 1, but not 1. If it's a minus, it doesn't equal 1.
Yeah, I don't. Yeah, sine squared plus cosine squared would be 1, but not with a minus in here. Right off the top of my head, I can't think of any trig rule here that's going to help us. But I've been wrong. I mean, I don't see one though.
I was probably just getting the one mixed up with tangent. As a cosine squared and sine squared is something.
Yeah. All right. So, what we need then, if we want the slope to be 0, then that we want to find the values of x that make this true. All right. Can we agree that this is only going to be true, like we can divide it by negative 3, 0 equals cosine squared minus sine squared? Does that make sense? Can we agree that we could move sine squared over to this side? Sine squared x, cosine squared x. Like that.
Wait, that makes sense.
Can't I just move this sine squared over to here?
Yeah.
Yeah?
Yeah, but like sine squared does not equal cos.
Sure it does. If cosine squared plus sine minus sine squared equals 0. Right? Maybe you were not noticing. So here's where we started something new, where we said, okay, now we're saying we want the derivative to be 0. We want the slope of the tangent line to be 0. Now we're finding the values of x to make that true. And it would appear that it's going to be any place sine squared equals, sine squared x equals cosine squared x. Yeah, but remember for trig, what angle has that the sine squared is equal to the well, here's the deal. Can we agree we can take the square root of both of these sides, and now we're saying when the sine x equals cosine x?
that'd be 45.
Yeah, it's on the 45s. It's at 45, 135, and the other two, who I always get wrong, 225 and whatever. Okay? So those are going to be the 4 angles we're talking about. They're going to be, because once we square, we lose the signs of this, the pluses and the minuses, right? Like this one right here, where the sign is negative, the sign is positive square root of 2 over 2, but the cosine is negative square root of 2. Well, once I square it, it gives a damn about the pluses and the minuses anyway, right? So it's going to be 45, 135, 225, and whatever the last one is. I always forget. 295, I think. Okay, so those are going to be the angles and so there's a pattern to it. All right, but it was this idea that, if we made a graph of this function, negative 3 sine x cosine x, it probably does something like this, and okay, but here, this is at like 45, well, let's do it in radians, then this is like, maybe this is negative pi over 4, this is at pi over 4, this is at whatever, okay? All right, you had a different one you wanted to talk about too?
Those are the only 3 exams. The other one was, what's the difference between b of y over b of x versus b over b of x?
Okay, good question.
Very good.
I like this. Tell me again, you want to know what's the difference between dy dx and what was the other one?
d over dx.
Yeah.
Just
Yeah. I wondered about this on Tuesday, and I had it percolating in the back of my brain to ask Jared what the difference was.
Of what?
The 2 things I wrote there on the board. dy dx and d of dx, or d by dx.
No.
Yes! Excellent answer. Because I'm a terrible teacher.
Oh, you taught us.
Oh, I taught you. I don't know about that.
Yeah, you did.
You taught us.
It's-
I just may have.
It's
forgotten.
Jared.
The one on the right is find the derivative of x, and then the one on the left is find the derivative of
Not quite.
y with respect to x.
This one here is an operator. It is an action. It's saying, find the derivative with respect to x of something. And you'll get an answer. It's an operator. It's do something to it. dy dx is something. It is something like dy dx turns out to be 2x plus 2. I mean, like, you could have dy dx in an equation. In fact, in the last section that we just did, the one with implicit differentiation, there were like move all the terms with dy dx over to the left-hand side of the equation. I mean, it's a thing. It's a placeholder. It's like a variable that holds dy dx. I mean, it holds 2x plus 2 in that case, okay? There's a value that goes in there. All right? So this is an action. Go do this. This is take the derivative of, and this is, no, I mean, we have this. Dy dx is equal to this. Or find dy dx given. That would be one way they would write it, right? Some of your problems are written something like, find dy dx given y equals x squared.
and how would we solve?
Well, then dy dx is the derivative of y with respect to x. So the derivative of y, well, y is equal to x squared. So we're taking the derivative of x squared with respect to x. So that would be dy dx is equal to 2x. These are excellent questions.
So dy dx is more or less just the f prime.
You're finding the answer. That is, dy dx is the derivative of y with respect to x. It is the derivative. The d by dx means like take the derivative. But here's the deal, they're not that different. I mean, when you have that little d, I'm sorry, when you have d by dx like this, d, which is pronounced d by dx, which is confusing considering the other expression is dy dx. They sound too damn much alike.
Do they
There's-
spell it the exact same way?
Yeah, I mean, they're just two, yeah, I mean, this is always going to have, like, the derivative with respect to x of cosine x. I mean, it's got right there what this acts on it, right? So this is saying find the derivative of this. So you can say, oh, derivative of this is equal to, derivative of cosine is negative the sine. It only gets to be a mess when there's, well, this notation is helpful when there's other things in here too. I mean, in the real world, of engineering, business, sciences, etc., those equations generally have more than just one thing in it, right? There's going to be x's and y's and z's and stuff like that. You need to know, am I talking about when I change the slope with respect to x, the slope with, the rate of change with respect to time, the rate of change with respect to temperature? I'm a meteorologist. Rate of change of pressure. Change in pressure with respect to time would be like as I stand right here and time goes by, is the pressure going up, is the pressure going down? Rate of change of pressure with respect to height means as I go up, how does pressure change? Rate of change of pressure with respect to temperature means as it gets warmer, how does the pressure change? That kind of thing. Only in like when you have applications that there's lots of different variables does this notation suddenly become so obvious why that's important. Okay? At the level of we're doing it right now, when we're always taking the derivative with respect to x, it kind of becomes, that's why the book likes the tick marks better. Wow, great! Wow. All right, we only have one lecture left, I mean, one section. And then hypothetically on Friday we're taking a review, and then on Tuesday we are hypothetically taking a test. I say hypothetically because kind of depending on how the review goes and stuff like that, we might put the test off until Thursday and do more reviewing on Tuesday. But I actually have kind of the feeling that this is going well. Okay, as far as I can tell, it's just rules and you apply the rules, and as long as you're careful about playing the rules, how should I put it? That's what students are good at. That's what everybody's good at.
Yes.
Yes. So I'm actually thinking that putting this test off is not necessarily helpful.
No.
So wait,
Fantastic.
I got a question.
Sure thing.
Did you know that brushing your teeth is the only time you clean your skeleton?
Sometimes I wonder what Jared is doing over there with his computer open.
It just
So-
popped up.
That would
You know,
imply
like
the
a-
teeth are bones, and they're not. Well, I don't know. It actually is. It
They
doesn't-
are bones.
Teeth aren't. I have a dentist for a wife.
My mom.
your
Really?
mom is a nurse.
My mom's a dentist.
A dentist, really?
Yes.
Oh, okay.
Your mom is a dentist? I did not know that.
Works for Woodyard Paradise.
Oh my goodness, okay. My wife refers then often there. All right,
Gum disease.
that's right. Okay, real quick. The last section of this book, of this chapter, is just derivatives of logs and derivatives of exponentials. And it's not that hard of a thing. Remember, like an exponential is when you have something like e to the x. Remember e from back in like pre-calculus and stuff like that? It's Euler's number 2.713 or something. I can't remember off the top of my head. All right. It's got a really funky derivative. But if that's what if your exponential is, if your function is that, the derivative is the same damn thing. In fact, that's another way to define e. E is the only function who's its own derivative.
But it's not a constant.
E is a constant. Yeah, but if you wanted to describe it as like an exponential function, what function is its own derivative? The only one that works is e to the x power. And if you think about what the graph looks like of this, it actually kind of makes some sense. Let's see here. How do I want to... Let's see. It goes through... It goes through like this. So, like, as the function gets bigger and bigger, the slope gets steeper. I didn't draw this very well, but whatever. Anyway, the slope, the farther out you go on the x-axis, where e of x would be a big number, then your slope is also getting bigger and bigger. Alright, it's just pretty neat. You really won't see, like, I doubt you have any problems in the book that are as simple as just e to the x, but they'll be more fun. They'll have it in there. Like, what if f of x was equal to, I don't know, e to the x times cosine of x?
Maybe e to the x times negative sine x.
Okay. Because, wait, whoa. No. It's a product rule. Here's our first thing, here's our second thing. So, derivative of the first, but derivative of e to the x is just e to the x, times the second, plus the first, times the derivative of the second, which means negative sign. And now we can factor that e to the x out just to be happier. There you go. Now, you can imagine things go nuts with these things. But applying your quotient rule, your product rule, whatever. The issue is, what if it isn't e to the x? What if it is e to some function of x? Let's see here. For example, what if it was f of x equals e to the 2x? What I want you to notice is it's not e to the x, it's e to something that depends on x, to some function of x. And I'm going to write this out a little bit different. Let's make this more general. Let's say e to the g of x. It's e to some function of x. Well, its derivative then will be, it's actually just an application of the chain rule. It's a derivative of the outside part, which is e to the g of x, times the derivative of the inside part. It's just a chain rule. It's just it's hard to think about it as a chain rule. So like in this case, where e to the 2x, the derivative of that would be e to the 2x times 2. E to the g, e to that function, times the derivative of that function. So that'd just be, 2e to the 2x. If we're learning about exponentials, you know where we're going with this. We're also going to do logs. What if your function was the natural log of x? This one is weird. The derivative of x then is 1 over x, or x to the negative 1 power. That one kind of weirdly breaks the pattern. I mean, before I put this up there, you've known lots of times that, like, for example, if we had x squared with our function, you knew, let's make it x cubed as our function, you knew you pull that number out in front and you lower this by 1. We never had a problem where it was x to the negative 1, but we could have. And you would have been not surprised. You probably would have said, okay, it's got to be, I guess it comes from x to the 0, because we're going to look. Well, wait a minute. If we had a term that was x to the 0, we'd be pulling the 0 out in front, 0 times x to the negative 1, but that would just be 0. Something's wrong. Turns out that's because that one doesn't work. You go from natural log to x to the negative 1. Okay. So the derivative of natural log is x to the minus 1. Now, again, we can do this all over the place with examples. We can have f of x equals 3 natural log of x plus x squared. Well, then its derivative would be 3 times 1 over x plus x, 2x. And your book will have some examples like that. And that's not so hard. What's going to get a little trickier is when you have functions where it's not the log of x, where it's the log of something that depends on x. Oh, I don't know. F of x equals the log of the cosine of x. Let's write that more generally. What if we said that that was like the log of some other function g of x? And again, in a bright blue box on page, I guess it's 325, you actually would see that the derivative of something like this is, again, it's just a chain rule, but it can be a little hard to see how it works. So like 1 over g of x times the derivative of g of x. So like in this case where g was cosine of x, this is 1 over the cosine of x times the derivative of cosine, which is negative sine. So this is negative the sine of x over the cosine of x. Or in this case, how weird is that? It's tangent. They're just more strange chain rule problems. Now, your book does then go into here and start saying, but you know, there's all those other things. I mean, this is natural log, and this was natural exponentials, like e and natural log. And now you remember back to pre-calculus, and you start getting chest pains because you remember that there were logs of different bases and all that kind of crap. Here's the deal. Rather than sit here and dump all that on you, I'm going to point you to page 326 and 327, the rules for when it's not the natural log. Well, what if f of x was like the base 10 log? Or worse yet, what if it was the base, I don't know, 7 log? All those weird, stupid bases that we learned about in pre-calc that don't actually happen all that much in the real world. I'm not going to take your time. If any problems like that come up in the chapter, just go plug in the formula you see on page 326. 326 to 327. There won't be problems that involve, what is f of x is the log of base 7 of x. No, that never happens in anything except a math class. Okay, so we're not going to worry about that. Okay, so for today's assignment, let me pull it up. Alright. Oh yeah, okay. So today, page 331. I don't know why I thought that was interesting, but on page 331, we're doing problem number 331 through 359I. So that's your assignment to bring tomorrow. Now, let me just look at the grade book real quick. All right, so that's everything that you guys need. I'm going to stop the recordings, and then we will start looking at